So I'm going to do one more related rates example, and this is one that is a little more complicated than the others because um, there's a couple of different relationships going on between our variables. So what are we trying to find? We're still going to read through the problem. How fast is the water level rising? So I'm going to call that dH dt. And then here's a picture of what's happening. In this picture, the radius is changing as the water fills up. The radius of the height of the cup is not changing, but the radius of the water is changing. So I'm also going to put the radius of the cup, which is not changing. The radius of the cup is 2. That's going to be a number, but the radius of the water is changing. And then the height of the cup is not changing. The height of the cup is 6. But the height of the water is changing. The height of the water is h. And I'm trying to indicate this part, but you can't see my writing on the blue there. Okay. So there are two different relationships that we have. One of the relationships is between the volume, because we have this rate of change in the volume, and the height. And so that relationship for a cone is 1/3 times the area of the base, since it's a circle, pi r squared, times the height. That's not a formula that we expect you to have memorized. So if you didn't remember the formula for a volume of a cone, that'd be okay. We'd give you that. But here's the tricky part. There's also a relationship, because this is 1, 2, 3 variables. So there's another relationship that we can use, and that relationship is, imagine that I just took this triangle and looked at that triangle. So the dimensions of that triangle are 2 by 6. And then also the water forms a triangle. And so that the dimensions of the water triangle are R and H. But those two triangles are similar because they share an angle, and these two lines are parallel, so they share another angle. And so they're similar triangles, so we can also say that the sides are proportional. So 2 over 6 is equal to R over H. Or another way of saying that is that 2H equals 6R, or that H equals 3R. But actually, I don't want to solve this for H. I would like to still have an H in my equation. I don't want to have an R in my equation. So I'm actually going to look at this as R is equal to H over 3. So this particular situation has two different relationships that we're looking at, and we can use that second relationship to make our volume equation a lot more simple. So if I see my radius is not r, but it's h over 3 squared, then I have 3 times 9 would be 27th pi, and then h squared times h would be h cubed. So now my volume equation only has two variables. It has the volume variable and the height variable. So then we're going to do calculus on that relationship. So dv dt equals 1/27th pi times 3h squared times dh dt, or pi over 9 h squared times dh dt. And now the plug and chug box, we're going to fill in how fast is the water level rising when the water is 4 inches deep. So we're going to fill in. And then we also have this piece of information. So dv dt is 2/3 inches cubed per second. And that equals pi over 9 times h, which is 4 inches squared, times dh dt. So we have 2/3 inches cubed per second This would be 16 pi over 9. So I'm going to do the reciprocal. 9 over pi times 16 inches squared. And our inches units cancel a bit. So we just have inches per second, which is what we want it to be for DHDT. And then this 3 can cancel with this 9, and this 2 can cancel with the 16. So we have 3 over 8 pi inches per second is going to be our rate of change on the height. So cone problems tend to be a little bit more involved because you have two relationships that you're looking at.